Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is Digital 1. Today we're going to discuss binary arithmetic and the very important concept of the 2's complement. And this is the chapter where I like to say that we separate the need to know from the nice to know. Because there's a lot of things that are nice to know, but ultimately they end up to becoming binary party tricks that are not really essential to your understanding at this level. So, first thing we need to do is introduce, well, our basic decimal addition, basic decimal multiplication, because we all know that regular 2 plus 2 is 4, right? 2 times 3 is 6. But this could easily be rephrased as 2 plus 2, which is 4, plus 2, which is 6. 2 taking it 3 times. So multiplication, all it is a subset of addition. It's doing addition a number of times, okay? So if we know addition, we don't need to know multiplication. Now, what if I was to tell you, using some binary devices, I can do subtraction using addition? And I know you may be thinking, all right, Jim has gone off the deep end on this one, but trust me, and I'm going to show you how it's done. I can subtract using addition, okay? But now think of division. Division is just a subset of subtraction. So if I can subtract using addition, I can also divide using addition. So if I understand addition, I can do addition, multiplication, subtraction, and division. Okay, so all I need to do is know addition. And let's go ahead and review this here. This may be a review for some of you. Okay, so binary addition. 1 plus a 1. Just like decimal addition, 1 plus a 1. And again, this is base 10, that's base 2. 1 plus a 1 in base 10 is going to give us a 2. A 1 and a 1 in base 2 is going to give us the binary equivalent of decimal 2, which is 1, 0. Okay, so what you're doing is you've got a 1 and a 1 added together, which is going to give you a 0, and you've got a carry of 1. So here's our sum, and here's our carry out. Okay, this will become critical later. You don't have to worry about carry out and sum just yet. Okay, and our decimal, 2 plus a 1 is a 3. So 1, 0 plus a 1 is also a 3. So a 1 and a 0, that sum is a 1. And bring this 1 down. Okay? Just think of 1, 0 plus a 1, 0. A 0 and a 0 added together is a 0. A 1 and a 1 added together is a 0 with a carry of 1. Okay? And very similar to this occurrence right here, let's say we've got a 1, 1, which is a binary equivalent of 3. We're adding it with a binary equivalent of 2. 1, 0 added together is a 1. A 1, 1 added together is a 0 with a carry of 1, which would drop down, which gives us the correct answer. You can always check your work. 3 plus 2 should be equal to 5. Key point is every time you exceed the number of spaces, here we've got a 3 plus a 2, we've got to go to the next higher positional place there. So we're going to keep on expanding into that, okay? So we've got some general rules where a 1 and a 0 added together is a 1. A 0 and a 0 added together is a 0. A 1 and a 0 and a 1 added together is a 1. And a 1 and a 1 added together is a 0 with a carry of 1, okay? So critical to your understanding there, okay? So now you can expand this. Let's pretend we're going to do 4-bit numbers. Let's add 0, 1, 0, 1, which is 5. And let's add that with another 5, just for the heck of it. So if we do everything correctly, our answer should be the binary equivalent of 10. So 1 and a 1 added together is a 0 with a carry of 1. A 0 and 0 added together is a 0, but we've got this carry of 1, so that's a 1. A 1 and a 1 added together is a 0 with a carry of 1. 0 and 0 added together is a 0, but you've got a carry of 1. 1, 0, 1, 0, we're correct. That is binary equivalent of 10. Okay? Let's try this one. Let's add 6 plus 14. Decimal, that's pretty easy, 20. Let's go ahead and do this in binary though. So 6, there's no 8s, there is a 4, there's a 2, there's no 1s. 14, there is an 8, there is a 4, there's a 2, there's no 1s. So a 0 and a 0, that's a 0. 1 and a 1, that's a 0 with a carry of 1. And now here comes a new problem. A 1 and a 1 is a 0 with a carry of 1, but we've got a carry in of 1. So if 1 and a 1 was a 1, 0, and you've got a carry in of 1, your answer should be 1, 1. 1, and that other 1 carries out. So now here, we've got a 1 and a 0 added together, which is a 0. Or excuse me, which is a 1. But then we're adding another 1 to that. So that's a 0, 1, or excuse me, 1, 0. So we've got a carry out of 1. Okay? What we're adding in is another place there. So we've exceeded the maximum amount, the number that can be represented in a 4-bit number. Okay? Because 20 can't be represented in 4 bits. So we have to go on to the next level, adding a 5th bit on there, or adding another 4-bit package, making our total our 1 byte or 8-bit package. Now be aware, if you are limited to only 4, that's what's known as an overflow error. Because if you're limited to only 4 bits, expressing your answer as 4 bits, what is your answer? Well, it's 4. 6 plus 14 is not 4, it's 20. So you need to have 8 bits to properly, or in this case 5 bits to properly represent it. Okay, so be aware that overflow can exist. Okay, so that's basic addition. Now, like I said, multiplication is just a subset of addition. So let's do 2 times 3. That's the same as 2 plus 2, which is 4, plus 2, which is 6. Let's see if that's true. So 1, 0, plus 1, 0, 0, 1 and a 1, 0, carry out of 1, 1. That is 4. Plus 1, 0, 0 and a 0 is 0, 0 and a 1 is a 1, and a 1. Tack that on there to make a nice 4-bit number. What does this represent? No 8s, a 4, and a 2. It's equal to 6. Okay? So that's what a machine is doing. It's basically doing successive addition to perform multiplication. Okay, now let's use addition to do subtraction. And I'm going to put a line here because there's 2 different worlds. This is regular binary. This is what's known as 2's complement. Okay? 2 totally different languages using the same characters. Very similar to English and Spanish, using the same letters. 2 totally different languages. And the question is always asked, how do I know when a number is straight binary or 2's complement? I'm going to tell you. Okay, so don't just assume that a number is 2's complement or binary or BCD or gray code or any of those other things that we talk about later on in lecture. I'm going to tell you what language you're speaking. So just as one would show up in Barcelona, you would expect they'd be speaking Spanish. You show up in the United States, you'd expect they'd be speaking English. You'd know which language you're going to speak. Okay, so 2's complement. What is 2's complement? 2's complement is the representation of negative numbers, okay, using a special technique where the leftmost bit, i.e. the MSB, in this particular case, let's do a 4-bit representation. 2 to the 3, 2 to the 2, 2 to the 1, 2 to the 0. The leftmost bit, this guy, is a negative number. So, -8 plus 4 plus 2 plus 1. Okay, so anything in this spot right here, if there's a 1 in that spot, it means you add -8 to the number. Okay? And if we were to do this in 8-bit representation, 2 to the 0, 2 to the 1, because there's a difference between 4-bit 2's complement and 8-bit 2's complement, which you'll see. 2 to 3, 2 to 4. Here's our 4-bit group. Here's our 4-bit group. What is this? That's a negative number there. All these guys are positive. This leftmost bit is a negative number. So that's a 1, 2, 4, 8, 16, 32, 64, -128. Okay, how does this come into play? Okay, let's say I want to subtract, let's say 6 minus 3, which we all know should be 3. This is how you do it in binaries 2's complement. Take 6, and let's say we're going to stick to 4-bit here. Just take 6, make its binary equivalent. Take 3, and because it's a -3, get its 2's complement representation and add them together. Get your answer and discard the last bit. And that's how you perform subtraction using, as I said, addition. Okay, so how do we get the 2's complement representation of a number? First off, and this is steps, and I'm going to ask you to do this on exams, quizzes, and labs. So write this down. So how do you get the 2's complement of a number? Get the straight binary representation. In this particular case, we're using 4-bit representation of 3 is a 0, 0, 1, 1. That's step 1. Step 2, invert it. Invert it takes the opposite of what you have. A 0 becomes a 1, 0 becomes a 1 becomes a 0, a 1 becomes a 0. Step 3, add a 1. Plus 1, 1, 1, 0, 1. This is the 2's complement representation of -3. Is that true? Well, if this represents -8 plus 4 plus 1, -8 plus 5, -3, we are correct. Okay? So let's go ahead. We've got the 2's complement. Putting it back into our steps here, so we've got our straight 6, the 2's complement representation of -3, which if we remember right is 1, 1, 0, 1, 1, 1, 0, 1. Add it together, 0 and a 1, 1, 1 and a 0, 1, 1 and a 1, 0, carry 1. 1 and a 1, 0, carry 1, which goes here, discard last bit. Our answer, 0, 0, 1, 1, which if you remember right, is 3. Okay, always check your work when you're doing this. Okay, so another quick example of this guy. Let's do, I don't know, like 8 minus 2. Okay, so 8, 1, 0, 0, 0. And again, we're using 4-bit representation of these. Minus 2. Okay, so 2 regularly is 0, 0, 1, 0. And according to our instructions right here, we need to get the straight binary representation of it. Step 2, invert it. 1, 1, 0, 1. Step 3, add a 1. Plus 1. 1 and a 1, 0, carry 1. 1, 1, 1. The 2's complement representation is 11110. Put that in there. 1, 2, 3, 0. Add them together. 0, 1, 1, 0. Carry 1. Discard. What is our answer? Our answer is there's a 4, there's a 2, 6. 8 minus 2 equal to 6. It makes sense. So now there's a disadvantage when you're using the 2's complement representation of numbers, because if I was to go ahead, here I'm just going to write a table of, in this particular case, let's do 4-bit. So here's all possible combinations of a 4-bit number. So as you can see, we're limited to this particular combination. So there's no other combinations of 1s and 0s that can fit inside a 4-bit number. So as you can see there, we're limited to basically the number of numbers we can represent. So in straight binary, that's a 0, 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. Now, that's regular binary. In 2's complement, we don't have the same range as we do in regular straight binary, because these numbers are the same. The first 8 are. But what happens here? Something different happens, basically. This is, if this position represents a -8, what is that? Oops. Okay, so this represents -8. -8 with a positive 1, so that's a -7. Oops, not sure what's going on there. -6, -5, -4, 3, -2, -1. As you see, we can't represent the same range of numbers in 2's complement for the same number of bit positions. Okay? And I'm going to put these guys where they belong, hopefully. Right here. Okay, so for 4-bit binary, we can represent the numbers 0 to 15. For 4-bit 2's complement, we can represent a range of numbers -8 to +7. It's the same number of positions, i.e. 16 positions. Still 16 positions. But our range of numbers, the maximum we can go to is +7 for a 4-bit 2's complement down to -8, whereas we can go from 0 to 15. So this is somewhat complicated if you're using, how would you represent, here's a classic example, how would you ever represent -9 using 4-bit 2's complement? it just wouldn't work, because here's what would happen. There's regular 9. You invert it, 0, 1, 1, 0. Add a 1 to that guy. That's a 1, 1, 1, 0. Does not compute. Because what is that? That's positive 7 right there. So that's 9, and you're trying to improperly represent it in 2's complement using a 4-bit number. It just wouldn't work. So how would you do that? Expand it to 8-bit 2's complement, which is, I've inverted it. Now I add my 1. That is the proper representation of -9 using 8-bit 2's complement. Okay? So please, by all means, learn how to use 2's complement to perform subtraction. And again, like I said, if addition is, if multiplication is a subset of addition, division is a subset of subtraction. Okay, so if we do successive subtractions using 2's complement representation of numbers, we can go ahead and perform division. Okay, so this is, again, I'm separating the nice to know from the need to know. And you're going to get some neat time-saving devices using 2's complement representation to perform subtraction, actually using addition. Okay, so we're going to go on to our next lecture, which is going to talk about some of the codes that you can use with binary numbers.